All right, like I said, we're going to finish off Chapter 9, Counting and Probability, this session and the next class session. Today we're going to be talking about R combinations with repetition allowed. In this section we ask, how many ways are there to choose R elements without regard to order from a set of n elements if repetition is allowed? A good way to imagine this is to visualize n elements as categories of objects from multiple selections, from which multiple selections may be made. Definition and notation. An R combination with repetition allowed, or multiset of size R, chosen from a set X of n elements, is an unordered selection of elements taken from X with repetition allowed. If X equals X sub 1, X sub 2, etc. to X sub n in curly braces is the set notation format and notation. We write an R combination with repetition allowed or multiset of size R as X sub I 1, X sub I 2, etc. to X sub I j. And those are listed in square brackets, where each X sub I sub j is in X, and some of the X sub I sub j may equal each other. So, write a complete list of to find the number of 3 combinations with repetition allowed, or multi-sets of size 3 that can be selected from the set of 1, 2, 3, and 4. Observe that because the order in which the elements are chosen does not matter, the elements of each selection may be written in increasing order, and writing the elements in increasing order will ensure that no combinations are overlooked. So you do all the combinations that start with 1, 1, all the combinations that start with 1, 2, all the combinations that start with 1, 3 or 1, 4, all the combinations that start with 2, 2, etc., going through, and you count them up, and there are 23 combinations with repetition allowed. Theorem 961, the number of R combinations with repetition allowed that can be selected from a set of n elements is R plus 1, or R plus n minus 1, choose R. This equals the number of ways R objects can be selected from n categories of objects with repetition allowed. So, kind of a complicated counting exercise here. A person given a party wants to set out 15 assorted cans of soft drinks for his guests. He shops at a store that sells 5 different types of soft drinks. How many different selections of cans of 15 soft drinks can he make? If root beer is one of the types of soft drinks, how many different selections include at least 6 cans of root beer? If the store has only 5 cans of root beer but has at least 5 or 15 cans of each other type of soft drink, how many different selections are there? For A, think of the 5 different types of soft drinks as the N categories, and the 15 cans of soft drinks to be chosen to be the R objects. So N equals 5 and R equals 15. Select each selection of cans of soft drinks is represented by a string of 5 minus 1, or 4, equal vertical bars to separate the categories of soft drinks, and 15 crosses to represent the cans selected. For instance, this string here represents a selection of 3 cans of soft drinks of type 1, 7 of type 2, none of type 3, 3 of type 4, and 2 of type 5. The total number of selections of 15 soft drinks of the 5 types is the number of strings of 19 symbols, 4 of them vertical bars, and 15 of the X symbol, equals 15 plus 5 minus 1, choose 15. Or 19 choose 15, which is 19 factorial divided by 15 factorial times 19 minus 5, or minus 15 factorial, which comes to a total of 3876 combinations of soft drink. Part B, if at least 6 cans of root beer are to be included in the selection, you can imagine choosing 6 such cans first, and then choosing 9 additional cans. The choice of the 9 additional cans can be represented as a string of 9 X's and 4 vertical bars. For example, if root beer is type 1, then the string here represents a selection of 3 cans of root beer in addition to the 6 cans originally chosen, and none of type 2, 2 of type 3, 4 of type 4, and none of type 5. Thus, the total number of selection of 15 cans of soft drinks of the 5 types, including at least 6 cans of root beer, is the number of strings of 13 symbols, 4 of them vertical bars and 9 of them X. So you would have 9 plus 4, choose 9. Or 13, choose 9, which is 13 factorial, divided by 9 factorial times 13 minus 9 factorial, which is a total of 715 combinations. If the store has only 5 cans of root beer, then the number of different selections of 15 cans of soft drinks of the 5 types is the same as the number of different selections that contain 5 or fewer cans of root beer. Let T be the set of all possible selections, assuming that there are at least 15 cans of each type. Let R sub less than or equal to 5 be the set of selections from T that contain 5 or fewer cans of root beer. And let R sub greater than or equal to 6 be the set of selections from T that contain 6 or more cans of root beer. Then T would equal the union of both of those sets. And the intersection of the two sets would be the empty set. By part A, the number of total combinations possible is 3876. And by part B, R sub greater than or equal to 6 equals 715. Thus, by the difference rule, n of R sub less than or equal to 5 equals 3876 minus 715, or 3161. So when there are only 5 or fewer cans of root beer, number of different selections of soft drinks is 3161. Counting triples. If n is a positive integer, how many triples of integers from 1 through n can be formed in which the elements of the triple are written in increasing order but are not necessarily distinct? In other words, how many triples of integers I, j, and k are there with 1 less than or equal to I, less than or equal to j, less than or equal to k, less than or equal to n? Any triple of integers with those conditions can be represented as a string of n minus 1 vertical bars and 3 crosses, with the positions of the crosses indicating which 3 integers from 1 to n are included in the triple. Table illustrates this for n equals 5 and a couple of examples of that, how it could be divided. Thus, the number of such triples is the same as the number of strings of n minus 1 vertical bars and 3 x's, which is 3 plus n minus 1, choose 3, or n plus 2, choose 3, which, when you multiply it out and do some cancellation, ends up being n times n minus, or n plus 1 times n plus 2 all over 6. How many solutions are there to the equation x1 plus x2 plus x3 plus x4 equals 10 if x1, 2, 3, and 4 are non-negative integers? Think of the number 10 as divided into 10 individual units, and the variables x1, x2, x3, and x4 are as 4 categories into which these units are placed. The number of units in each category, x sub I, indicates the value of x sub I in a solution of the equation. Each solution can, then, be represented by a string of 3 vertical bars to separate the 4 categories, and 10 crosses to represent the 10 individual units. For example, the following table, 2 crosses under the x1 and 5 crosses under x2 and 3 crosses under x4, represent the solution x1 equals 2, x2 equals 5, x3 equals 0, and x4 equals 3. So, yeah. Therefore, there are as many solutions to the equation as there are strings of 10 crosses and 3 vertical bars, namely 13 choose 10, 13 factorial divided by 10 factorial times 13 minus 10 factorial, which multiplied out equals 286. Remark, deciding which formula to use. Kind of an important one. Got to know when to use which one. Earlier, we discussed 4 different ways of choosing k elements from n. The order in which the choices are made may or may not matter, and repetition may or may not be allowed. The following table summarizes which formula to use in which situation. I'd recommend making a note of this little table. Repetition is allowed, but order matters, then it's n to the k. If repetition is allowed, order does not matter. K plus n minus 1, choose k. If repetition is not allowed, p of n and k, and order does not matter. If repetition is not allowed, n choose k. Okay, Chapter 9, Section 7. Pascal's formula and the binomial theorem. And you thought you had gotten away from the binomial theorem in Algebra 2. But here it is again. So, in this section we derive several formulas for the values of n choose r. The most important is Pascal's formula, which is the basis for Pascal's triangle, and it is a crucial component of one of the proofs of the binomial theorem. We offer 2 distinct proofs for both Pascal's formula and the binomial theorem. One of them is called algebraic because it relies to a great extent on algebraic manipulation. And the other is called combinatorial because it is based on the kind of counting arguments we have been discussing in this chapter. Pascal's formula. Pascal's formula, named after the 17th century French mathematician, is one of the most famous and useful in combinatorics, which is the formal term for the study of counting and listing problems. It relates the value of n plus 1 choose r to the values of n choose r minus 1 and n choose r. Specifically, it says that n plus 1 choose r equals n choose r minus 1 plus n choose r, whenever n and r are positive integers with r less than or equal to n. This formula makes it easy to compute higher combinations. In terms of the lower ones, if all values of the lower ones are known. So this slide is kind of screwy on this in this program. Looking at it in PowerPoint, it'll probably come out right. But this is Pascal's formula, or triangle. It's a geometric version of Pascal's formula, where you can see that five choose 3 is 4 choose 3 plus 4 choose 2, or n plus 1 choose r equals n choose r plus n choose n minus I'm sorry, n choose r minus 1. Sorry, tripped over my tongue there. Sometimes it is simply called the arithmetic triangle because it was used for centuries before Pascal by Chinese and Persian mathematicians. But Pascal discovered it independently, and ever since 1654, when he published a treatise that explored many of its features, it has generally been known as Pascal's triangle. Pascal's triangle to compute the values of 6 choose 2 and 6 choose 3. Well, by construction, the row value in row n and the column R of Pascal's triangle is the value of n choose r for every pair of positive integers with n and r, with n r being less than or equal to n. By Pascal's formula, n plus 1 choose r can be computed by adding together n choose r minus 1 with n choose r, which are located directly above and to the left of n plus 1 choose r. So 6 choose 2 is equal to 5 choose 1 plus 5 choose 2, which equals 15. And 6 choose 3 equals 5 choose 2 plus 5 choose 3, which is 20. Let n and r be positive integers with r less than or equal to n. Then n plus 1 choose r equals n choose r minus 1 plus n choose r. That's theorem 971, Pascal's formula. Use Pascal's formula to derive a formula for n plus 2 choose r in terms of the values of n choose r minus 1, and n choose r minus 2. Assume n and r are non-negative integers, and 2 is less than or equal to r, which is less than or equal to n. By Pascal's formula, n plus 2 choose r equals n plus 1 choose r minus 1 plus n plus 1 choose r. Now apply Pascal's formula to n plus 1 choose r minus 1 and n plus 1 choose r, and substitute into the above to obtain this. Looks like a little bit much, but it can be simplified by combining these two terms here. to be n choose r minus 2 plus 2 times n choose r minus 1 plus n choose r, like here, for all non-negative integers, n and r, such that 2 is less than or equal to r, less than or equal to n. Now the binomial theorem. In algebra, a sum of two terms, such as a and b, is called a binomial. The binomial theorem gives an expression for the powers of a binomial, a plus b to the nth power, for each non-negative integer n and all real numbers a and b. Gives it in the form of a summation, where it goes from 0 to n, and it's n choose k times a to the n minus k times b to the k. So note that the second expression equals the first because n choose 0 equals 1, and n choose n equals 1 for all non-negative integers n, since b to the 0 is equal to 1, and a to the n minus n is also equal to 1. So for definition, for a non-negative integer powers of a recursive definition here, a to the n equals 1 if n equals 0. If n is greater than 0, a to the n equals a times a to the n minus 1. So expand the following expressions using the binomial theorem. Well, a plus b to the fifth power is just simply plugging in 5 into the binomial theorem, and you get a summation of k equals 0 to 5. 5 choose k times a to the 5 minus k times b to the k. And you end up with this when you expand and solve all the do the expansion and solve for the 5 choose 1, 5 choose 2, 5 choose 3, and 5 choose 4. And similarly with the second example. Now express the following sum in closed form without using a summation symbol and without using an ellipsis. Well, when the number 1 is raised to any power, the result is 1. So, summation of k from 0 to n of n choose k, 9 to the k, is equal to this here with the added term 1 to the n minus k, which can be used to do by the binomial theorem, where a equals 1 and b equals 9, make it 10 to the n, simply. Seeing that type of thing, it's kind of a, who thought of adding this term to make it work out that way? That's kind of a level of mathematical creativity that I just don't have. So I don't see that, see where you can add terms to make things simpler and all that sort of stuff. I don't, that's a little bit beyond me, and all that sort of stuff. But that about sums it up for the day. We're just going to cover the 2 sections today and another 2 sections next Tuesday. Like I said earlier, Thursday we are off, and the following Thursday we are also going to be off. So enjoy the time off. Maybe work on chapters 6 and 7 as extra credit if you need extra points on quizzes or test grades. Those are not due until the 30th. If you have in the announcement that I sent out last week, if you have any missing quizzes or tests, please make arrangements to get those done before the end of next week. And also, was there anybody in here that is going to be going out of town before the end of finals week? Okay. If you are, come see me next week in the morning sometime. We can take the final before finals week so you don't miss it. Anybody else going out of town before the end of finals week? Okay. All right. Well, don't forget the extra credit for the final exam as well. How many different ways you can have Waffle House hash browns. Personally, it was chunked in country for me this morning. But anyway, that's worth an extra 10 points on the final if you get it right and explain it properly. Not just the right number, but explain it and how you got the number and the final result. So, little practical counting problem for you. Anyway, okay. Have a good day. See you on Tuesday.